Section 4.2, where today we're going to be comparing linear functions to exponential functions using some of the skills that we learned back in 4.1, okay? So let's start off just by looking at two different functions in which they're using the same row of x values, the same inputs, and then just giving us separate outputs, separate either f of x or g of x values, okay? So first of all, we're going to find the difference between the consecutive values of f of x, okay? So in looking those over, we go from 30 to 45, 45 to 60 to 75 to 90 to 105. Obviously, that difference is constant, okay? So there is a constant difference, and it appears to be a positive 15, right? So now let's find the difference between the consecutive values of g of x, okay? We see that there's an increase of 200, then of 240, then of 200 and, mental math can be tough, 288, okay? And then for these last couple, let's go ahead and grab our calculators, okay? So let's start writing these down. 200, we said 240, 288. Now let's start taking these values and subtracting the prior value, okay? So we're going to take our 2073.6 and subtract off our 1728, and we're now getting 345.6. And finally, 2488.32 minus 345.6. And, oh, my bad. Not 345.6, but rather 2073.6. All right, and so we're getting that difference of 414.72, okay? So what do we notice? Obviously, f of x had a constant rate of change. Constant. And you know what? Let's not even use the word rate of change because that would be dependent upon us finding those input differences, right? If all we're finding are the consecutive values of f of x based on our table values, we're not really finding rate of change, the change in the output divided by those changes in, in input. So constant change for f of x. And then g of x, we clearly had increasing changes, right? So just kind of some broad generalizations based on what we've seen, okay? Now, we're going to find the ratio of consecutive values instead, okay? Well, what's the difference between, well, difference and ratio? Really what it comes down to is the operation that you're doing, right? If we're talking about difference, you're going to take a value and subtract the prior value in order to find, again, a 200, a 240, etc. Ratios, on the other hand, you would take the second value, let's refer to it as b here, divided by the prior value, in this case a, and then that's going to give us our ratio. Okay, so let's take our 1200, divide it by 1000, and we're getting a 1.2. Okay, from there, let's take 1440 and divide it by 1200. Once again, 1.2. 1728 divided by 1440. 1.2. I think we're noticing a bit of a theme. Let's just kind of jump to the end here and see if it's still holding true for those last couple values. 2488.32 divided by 2073.6. And once again, 1.2. So what this obviously tells us is that there is a constant ratio for g of x, right? Not a constant difference or constant change, but a constant ratio with regard to change. So kind of a big distinction. Again, one of those is going to create a linear set of values, whereas the other one creates an exponential set of values, right? So linear has a constant difference, and I'm sure many of you already know this, but that is referred to as the slope, right? So that multiplier, that m value, is really what created that constant difference of 15 for consecutive values, right? I will say, like I said earlier, it's a little bit more complicated than that. That's why I didn't use the term rate of change, because that would have been 15 divided by 5, which of course gave us a slope of 3. So that constant difference, just keep in mind, we're still referring to a rate of change there, okay? But this is kind of what it would actually behave as with regard to your general function. So what about exponential functions? Well, with exponential functions, pardon me, we obviously found a constant ratio of change. So there is a constant ratio between consecutive outputs. And I'm sure you guys are, already realized this based on the work we did last cycle, but that ratio is really essentially just your growth factor. That is your B value. And keep in mind, I'm not referring to this B. I just threw in two variables here so that we could calculate 1.2. This is actually the B value with regard to your general form, okay? So like I said, I hope that's starting to make sense, the key distinction between the two, okay? So let's look at a couple more tables of values. Number one here says that in some ways the formulas for linear and exponential functions are similar. In a linear function, y equals mx plus b, b gives us the y-intercept, right? And m tells us how the function is changing. In an exponential function, y is equal to a times b to the power of x. A is giving us the y-intercept, right, as we talked about last cycle, and b tells us how the function is changing. So it comes down to like where those changes are occurring, right? So determine whether the data in each table is exponential or linear, then identify the parameters of the function. So keep in mind, for a linear, our parameters are going to be m and b, right? Because we have to leave our input x and our output y open to create our set of points, all right? Separately, of course, we have our exponential. And so if you're dealing with your exponential function, y is equal to a times b to the power of x, we see that once again, leave your input and your output, your x and y open. That gives us parameters a and b, okay? So for this set of values, we're going to go about determining what type of function we're dealing with. Now here's the nice part. If you look at inputs, all of them have a constant difference of 1, okay? So there's going to be no sort of unusual division of values taking place here, okay? Let's go ahead and look at our change with regard to outputs now. 76 minus 65 comes out as 11. 85 minus 76 will come out as 9. 95 minus 85, well, that's coming out as 10. 105 minus 95 comes out as 10, right? Whether the data in each table is exponential or linear. Well, I'm seeing a bit of a problem, right? If we had 11 over 1 and 9 over 1 and 10 over 1 and 10 over 1, that seems really close to a constant difference. The obvious issue really occurred right here. If this was a 75 instead of a 76, we could actually fix this, okay? So let's go ahead, in order to create what it really needs to be between the two, it's really only mapping similarly to a linear. Let's go ahead and rewrite this as 75 and see what happens, okay? So 65, 75, 85, 95, 105. Now we're getting those constant differences of 10, right? So as you might imagine, if I were to take my change in output over change in input and it remains constant, we know that to be linear, right? So m is equal to 10. And then separately, our other parameter would be our y-intercept, right? So that y-intercept always has an x value of 0, and our output is our y-intercept. B is equal to 65, okay? So there's your set of parameters. And of course, we could say this was intended to be linear. Now, the truth is, that was a typo, okay? Apologize for the confusion there. But hopefully we can get that corrected, and we all understand why that makes a lot more sense. There certainly doesn't appear to be some constant multiplier, right? So kind of be aware. Pardon me. So on the next graph here, we've got 0, 1, 2, 3, 4. We've got 400, 600, 900, 13, 50, 20, 25. Well, let's look at some of those constant differences. Once again, these are all changing by 1, my inputs. Let's look at the change in the outputs now. From 400 to 600, it's an increase of 200, then 300, then 450, and then what appears to be 675. Okay, these are getting quite large quite quickly. So given that none of those are really all that similar, instead of finding constant differences, let's go ahead and try to find those ratios, okay? So again, with the ratios, you're going to take a value and divide it by the previous output, okay? So 600 divided by 400. And then we'll go from there, and we're going to do 900 divided by 600. And we'll do 1350 divided by 900. And finally, 2025 divided by 1350. We can just kind of see where this takes us, okay? Now, I'm sure many of you can do the first one in your head, but still. Not bad to get in the habit of just plugging these in and trusting our calculator with regard to the more complex calculations we'll be doing. So for the first couple, we got 1.5. 1.5. And once again, 1.5. So all of these have a constant ratio of 1.5. And just like we talked about before, our ratio is going to be our b value. B is equal to 1.5. That is not a y-intercept. And then for our y-intercept, our initial quantity that we talked about with regard to exponential functions, that's going to happen just like it did with our, our linear. So when x was 0, we had our output. When x is 0, we have our output. That, of course, is our y-intercept. So in this case, that's a value of 400. All right, so once again, exponential versus linear. As we said, some big similarities, but also some pretty sizable differences, okay? So that wraps it up for the first video. As we dive into the second, we'll take a look at some applications and kind of take it from there, okay?